The large machine company manufactures metal rods for large industrial equipment. Their standard manufacturing process produces rods whose lengths are normally distributed with a mean of 400 centimeters and a standard deviation of 5 centimeters. A rod is considered usable if its length is between 395 centimeters and 405 centimeters. Let X be a random variable denoting the length of a rod manufactured by the large machine company. Determine the probability that a rod manufactured by them is usable. Round your answer to 3 decimal places. So we know that X is normally distributed with a mean of 400 and a standard deviation of 5, therefore a variance of 5 squared. So we're just after the probability of X being between 395 and 405. So we can just evaluate that straight on the calculator. We need to go to, or I usually go to interactive, distribution, continuous, normal CDF, and we are going from 395 up to 405 with a standard deviation of 5 and a mean of 400. And that gives us 0.683 to 3 decimal places. Recently, the large machine company introduced a new manufacturing process that industry experts claim will improve the percentage of usable rods produced to 80%. The Quality Control Department decides to investigate whether this standard is being achieved and plan to collect a random sample of rods manufactured using the new process. What condition must the sample satisfy in order to use a normal distribution to model the sample proportion of usable rods? In other words, see if this claim is true. It needs to be a large sample. So let's just say large sample. I don't think we actually need to put a number on it. Normally they use n is greater than 30 for these sorts of things, but just large sample will probably do. The Quality Control Department collects a sample of 100 rods, so that should be fine if we think about this standard. What is the approximate distribution of the sample proportion of usable rods? So we know it's going to be, we probably shouldn't use X, let's use Y. So we know it's going to be normal because we've just been discussing that. And we're looking at 80% as being the claim. And therefore the variance is going to be 0.8 times 1 take away 0.8, which is 0.2, divided by 100. And so we get a normal with a mean of 0.8 and a variance of 0.0016. And of course, the square root of that is the standard deviation. Upon measuring the sample of 100 rods, it's found that 75 are useful. And that does work out to be 75% of them. 75 over 100 is our measurement of P. And so that is 0.75. We want to calculate a 95% confidence interval for the population proportion of usable rods. So we can state how that we would do that. So that's going to be 0.75. Take away the Z95 value multiplied by the standard deviation. And in this case, that's going to be 0.75 multiplied by 1, take away that, divided by 100. Note that is the standard deviation. We've got the square root there. And then we've got 0.75 plus exactly the same thing. So we wouldn't need to actually then calculate that on the calculator. We've got e-activities that can do this type of thing. So we'll go into the e-activities. So I think we can go in here, confidence interval for proportion. So we had 75 rods out of 100 rods. And we were using a 95% confidence interval, so we don't need to change that one. And that would give us this. Maybe I should have done the thing again in decimal. And that gives me 0.6651. Up to 0.8349. The quality control department would like to obtain a confidence interval with a smaller margin of error. In other words, they want one that's less wide than this. State two methods that they could achieve, they used to achieve this. Well, one thing is, we know that as the confidence level goes up, it gets wider. So reduce the level of confidence. Yeah, let's just say 90% there. That would do the trick. The other thing would be to increase sample size. If they do that, then the 100 that I just pointed to here gets bigger and makes the standard deviation smaller. And so we get a smaller confidence interval. Okay, so the quality control department decides to select a new sample for which the maximum possible margin of error for a 95% confidence interval is 0.05. What sample size will achieve this requirement? Okay, so we have an e-activity for this, but first we're going to need to go in here. We've already got 0.95, so I'm just going to press solve just to make sure that that value for Z goes into all the other ones. And then we've got a sample N for CI. So I'm going to write that formula down. N is equal to Z squared, P, 1 minus P, over E squared. So we know here that E is going to be 0.05. That's the margin of error. And we know that P is 0.75. Actually, correct that. I just reread the question. The maximum possible margin of error. So the maximum possible margin of error means use the largest possible standard deviation. So for that, we would take P is equal to 0.5 because 0.5 times 0.5 is bigger than, say, 0.75 times 0.25. So this one, the maximum possible margin of error, means we're going to use P is 0.5. And we've already got the Z score in here. And so what should we do? We're solving for N. We're going to put the P is equal to 0.5 and our E, we're going to make that equal to 0.05. Solve for N. And we get 384.14. And always round up in this situation, N is 385. The new sample yields the 95% confidence interval 0.717, 0.803. On the basis of this sample, is the proportion of usable rods different from what was claimed by the industry experts? Justify your answer. Well, we can see that 0.8 is contained in here. So we would not say that it was different. And we should also say that because 0.8 is in this interval, there would be insufficient evidence to conclude that the proportion of rods is lower than that which is claimed.